So we just covered what the term linear dependence means. Now we can say what linear independence means. Linear independence is the opposite of linear dependence. We call a list of vectors, v1, v2, up to vn, linearly independent if the only way to produce the zero vector with a linear combination of the vectors in your list is by forcing all of the scalars to equal 0. So linear independence means that c1 v1 plus c2 v2 up to cn vn equals 0 only works when you set all of the scalars equal to 0. So let's see an example where we actually verified that a list of vectors is linearly independent. Here my list of vectors is v1, v2, v3, where v1, v2, and v3 are these three vectors in R4. Well, how would I go about verifying whether or not this list is linearly independent? If you want to check that something is linearly independent, you have to start with one equation. And the equation you want to start with is the equation given by c1 times v1 plus c2 times v2 plus c3 times v3 equals the zero vector. You are interested in whether or not it's possible to achieve this equality using anything other than all of the c's equaling 0. And now the thing to notice is that by setting up this vector equation where the variables are c1, c2, and c3, we're actually defining a system of equations. So the system of equations has 4 equations with 3 variables. The coefficients in front of c1 are exactly the coordinates in the first vector. The coefficients in front of c2 are the coordinates in the second vector. And the coefficients in front of c3 are the coordinates of the third vector. And we know everything about systems. If we want to solve this system of equations, perhaps the best way to do it is to represent it with an augmented matrix. So now we're representing the data in the system with an augmented matrix. And notice that in the coefficient matrix of this system, the columns are exactly the vectors in the list that we are interested in. And how do we solve systems? We do row reductions. So let's say we do the row reductions. Well, I did them, and when I did them, I got this reduced row echelon form. The analysis here is straightforward. The system is certainly consistent because there's not a pivot in the augmented column. And critically, there are no free variables here. In fact, if you look at the 3 equations, the first equation is saying C1 has to equal 0, C2 has to equal 0, and C3 has to equal 0. So by setting up the equation that tests for linear independence, we are now arguing that the only way to achieve equality here is to force all of the C's to equal 0, and this means that the list we started with is linearly independent. Now, I want to point out here that in the process of going through this problem, what we're really doing is we're uncovering the fact that the matrix obtained by inserting the vectors we are interested in into the columns has a null space that only has the 0 vector in it. So this will end up being important in a moment. So again, if you care about whether or not a list is linearly independent, the place you have to start is this equation. Scale your first vector by a variable, scale your second vector by a variable, and so on. Add everything up and set it equal to 0. And the idea is that this will give you a system, and if your system has no free variables, then the list you're dealing with is linearly independent. Otherwise, the list will be linearly dependent. Here's another example. This one is more theoretical and less numerical. So here, what we're told is that we're starting with a list that is linearly independent, v1, v2, and v3. And what we're doing now is we're constructing a new list using the information we're given. The new list is w1, w2, w3, where w1 is v1 minus v2. So v1 and v2 are the first 2 vectors in our linearly independent list. w2 is our next new vector, and that's v2 minus v3. That's the second and third vectors on our linearly independent list. And then w3 is v3 plus v1. That's the first and third vectors in our linearly independent list. So we started with an independent list, and now we're curious whether or not this new list of vectors is linearly independent. Well, how do we go about solving this problem? We always start with the same equation. We want to know whether or not W1, W2, W3 is linearly independent. So we start with the equation where we scale the first vector we're interested in, W1, by a variable C1. Then we scale the next vector we're interested in, W2, by a variable C2. Then we scale the next vector we're interested in, W3, by a variable C3. We add everything up and set that equal to 0. Okay, so now we have to ask ourselves, what can we do here? Well, the first thing we can do is we can make our substitutions. W1 is equal to V1 minus V2, so let's sub that in. W2 is V2 minus V3, so let's substitute that in. And then W3 is V3 plus V1, let's substitute that in. Now what we can do is we can distribute these scalars and reorganize all of the coefficients. So how did we get from this first line to the second line? I distributed each of the variables here, C1, C2, C3, and then I reorganized the coefficients. On front of V1, I'll have C1 plus C3. On front of V2, we'll have negative C1 when I distribute, plus C2 when we distribute. And then in front of V3, we will have negative C2 plus C3. So now we get a new equation by starting with the relevant equation. But think about what we've done here. It might not seem like we've done a lot, but we've actually done something critical. We started with a list of vectors we're interested in, W1, W2, and W3. We set a generic linear combination of that list equal to 0. And by making our substitutions and distributing, we now realize that we're looking at a linear combination of the original list. The original list was V1, V2, and V3. And the scalars that we're now bumping into being used as our linear combination are C1 plus C3, negative C1 plus C2, and negative C2 plus C3. And this linear combination of the original list is now equal to 0. But we are told from the outset that V1, V2, V3 is an independent list. What this means is that the only possible way for this equation that we're using to work is if each of the scalars used in this linear combination equals 0. So I need this coefficient in front of V1, C1 plus C3, to equal 0. I also need the coefficient in front of V2, negative C1 plus C2, to equal 0. And then I need this coefficient in front of V3, negative C2 plus C3, to equal 0. And what have we bumped into? We've now bumped into a system of equations. And if I represent this system of equations with an augmented matrix, again, the equations are C1 plus C3 equals 0, negative C1 plus C2 equals 0, and negative C2 plus C3 equals 0, I can find the reduced row echelon form and figure out what the C's are. Here, when I take the reduced row echelon form, I get C1 has to equal 0, C2 has to equal 0, and C3 has to equal 0. And this is exactly what we need to conclude if we want to argue that the list we're studying is linearly independent. By setting up the equation that tests for linear independence, C1 times the first vector plus C2 times the second vector plus C3 times the third vector, and setting that equal to 0, we now run through an argument where the conclusion is that the only way for that to work is if the C's themselves equal 0.